You have just read the definition of a rational number. Remember that a rational number is a number that can be written in the form a over b, where a and b are integers and b is not 0. In other words, rational numbers are those numbers that can be written as fractions. What we're going to do is show that there are more numbers in the real number system than just the rationals. In other words, not all numbers can be written as fractions. Our first example of such a number is the square root of 2. A couple of notes before we start the proof. First of all, this result up here is something that we have proved earlier. N squared is even if and only if n is even. This result is not very interesting all by itself, but it will be required to do this proof. Since it is required to do this proof, but it really is of no big interest on its own, we take it out of the proof as a separate entity and call it a lemma. In other words, this lemma is very useful, it's very robust, but it's not exciting all by itself. But it can be used over and over and over again to prove theorems. Okay, so let's take a look at the statement here. The square root of 2 is irrational. In other words, it's not rational. This statement is a little different from the ones that we have dealt with before, because before we had if-then statements. If n is even, then n plus 1 is odd. This one is not really an if-then statement, it's just an assertion about the number 2. You take the square root of it, you get an irrational number. It can be forced into an if-then statement, but this sounds so much more simple. Whenever you have a statement like this, there is another proof technique that you have not seen before that will often be useful. It's called a proof by contradiction. The way it works is that we'll say, well, wait a minute, why is it irrational? Why don't we assume that it is rational? And then we'll play with it and do some algebra, do some arithmetic, and what will happen is we'll arrive at a contradiction. Since our assumption that the square root of 2 is rational leads to a contradiction, we'll be left with no choice but to assume that it is irrational. So here is our proof by contradiction. Suppose the square root of 2 is rational. Then, if it's a rational number, we should be able to write it as a fraction, a over b. Then the square root of 2 is equal to a over b, where a and b are integers, and b is not 0. Now let's take a look at a little aside example. Let's say a is 6 and b is 8. What can we do to this fraction? We can reduce it. We can factor out the 2 and cancel things out. So that's really 3/4. So if both the top and the bottom of the fraction are even, we can factor out 2, cancel it, and come up with another fraction. And we can keep doing that until these two have no common factors. Because as soon as you have common factors, you can cancel them out and keep going. So in addition to assuming that a and b are integers and b is not 0, we will also assume that a and b have no common factors, because if they did, we could just cancel them out. So moreover, assume that a and b have no so we have the square root of 2 is equal to a over b. The first thing we want to do is get rid of the square root. So why don't we square both sides? We get 2 is equal to a squared over b squared. And now I can multiply both sides by b squared, so I get 2b squared is equal to a squared. But take a look at this. This is an integer that's written in the form twice an integer. So this is 2 times an integer. So what can we conclude about a? We conclude that a squared is even, and therefore by the lemma, a itself would have to be even. So a squared is even. Therefore, a is even. And again, we can make this conclusion because we already proved the lemma up here. If the square is even, so is the number. All right, now since a squared is even and a is even, I can say then a is equal to 2k for some integer k. And now I'll take this 2k and plug it in. So what we have is 2b squared is equal to 2k squared, which gives me 2b squared is equal to 4k squared, and this gives me b squared is equal to 2k squared. But now, what do we have? What does this tell us about b? We have b squared is equal to twice an integer. 2 times an integer. This tells us that b squared is an even number. So b squared is even. And by the lemma, we conclude that b is also even. Therefore, b is even. So take a look at where this got us. We assumed that the square root of 2 was rational. We did a few manipulations, and in the process, we discovered that a has to be an even number, and then we discovered that b has to be an even number. So we have a is even and b is even. Think about all of our assumptions. Does this contradict anything that we know to be true? Remember, we assumed that a and b have no common factors. And here we have that both of them are even numbers, so both of them are divisible by 2. This is where we conclude that because we arrived at a contradiction, our initial assumption that the square root of 2 was rational is incorrect, and so it has to be irrational. So let's report this. But this contradicts our assumption that A and B have no common factors. So in this particular situation, we're done because we contradicted one of our initial claims, our assumption. Sometimes you end up going through a proof like this and you end up with something like 1 is equal to 2. Well, you know that that's not true, so again you have a contradiction because you ended up with 1 equal to 2. So what it is that you end up contradicting varies from proof to proof. In this case, you made a perfectly legitimate assumption that A and B have no common factors because if they did, we could just cancel them out. So we know that this can be satisfied. And yet at the end, it turns out that it wasn't. So that's our contradiction.